Inside a nondescript facility near Stanford, engineers are cooling a silicon chip to a temperature colder than deep space. Colder than the far side of the moon. Colder, in fact, than almost anywhere else in the known universe. This is a PsiQuantum cryo plant, and what happens inside it is central to one of the biggest technology bets of our time, the race to build a practical quantum computer. Quantum computing has become one of the hottest stories on Wall Street and in Washington. Some quantum stocks have surged more than 1,000% in the past 2 years. Governments around the world have pledged over $50 billion toward the technology. Tech giants, Google, Microsoft, Amazon, IBM, Intel, are all racing to claim breakthroughs. And yet, ask any expert a simple question. Can a quantum computer solve a real-world problem better than the laptop on your desk? And the honest answer, still, is no. Not yet. So which is it? Is quantum computing the next great technological leap, on the verge of transforming medicine, material science, and finance? Or is it, as one prominent skeptic put it, still decades away from mattering? The truth, as usual, sits somewhere in the noisy middle. A classical computer, like the one in your pocket, stores information in bits. Each bit is either a 0 or a 1. A quantum computer instead uses qubits, which can exist as a 0, a 1, or some blend of both at the same time, a property called superposition. Qubits can also be linked together through entanglement, letting a quantum machine explore a staggering number of possibilities simultaneously. In theory, this gives quantum computers the potential to solve certain problems, simulating molecules, optimizing complex systems, breaking modern encryption, that would take a classical supercomputer longer than the age of the universe. In practice, qubits are almost impossibly fragile. Dr. Elena Marsh, quantum physicist, fictional composite expert, on camera, a qubit needs to be almost completely isolated from the outside world to hold its quantum state. But you also need to control it, measure it, and pull information out of it. And the moment you touch it, in a sense, you risk destroying the very thing that makes it useful. This is the central paradox of quantum engineering: isolation versus interaction. Stray heat, vibration, electromagnetic noise, even a stray cosmic ray can knock a qubit out of its delicate state, a process called decoherence. When that happens, errors creep in, and the calculation falls apart. That's why PsiQuantum, and companies like it, spend so much effort and so much money on cooling. Superconducting qubits, one of the leading approaches used by Google, IBM, and others, must be chilled to about 15 millikelvin, a fraction of a degree above absolute zero, inside massive dilution refrigerators. But cooling is only part of the challenge. Today's quantum processors are also incredibly error-prone. Where a classical computer might make one mistake in a trillion operations, today's best quantum machines can make an error every few hundred operations. To do anything useful, engineers need to correct those errors faster than they occur, and correcting one reliable, logical qubit today can require bundling together dozens, even hundreds, of noisy physical qubits. That single fact explains most of the industry's roadmap. Before quantum computers can be useful, they need to get from a few hundred noisy qubits to potentially millions of high-quality ones. Superconducting qubits, tiny circuits etched onto silicon and cooled to near absolute zero, are the approach favored by Google and IBM. They're relatively fast and build on decades of chip-making know-how, but they demand extreme cooling and are notoriously sensitive to noise. Trapped ion systems, championed by companies like IonQ, use electromagnetic fields to suspend individual charged atoms in place, then manipulate them with lasers. Ions are naturally identical and long-lived, giving this approach some of the lowest error rates in the industry. But the laser systems needed to control them are complex and, so far, slower to scale. Neutral atom quantum computers, pursued by companies like Chuera and Atom Computing, arrange large arrays of atoms using laser tweezers. This approach has shown a path to scaling up qubit counts quickly, though keeping every atom perfectly controlled at scale remains a work in progress. Then there's the most contested approach of all, topological qubits, Microsoft's long-term bet. The idea is elegant: encode quantum information in the physical topology of exotic particles, making it inherently resistant to noise. If it works, it could sidestep much of the error correction burden altogether. The problem is that, when Microsoft announced a breakthrough topological qubit chip earlier in this push, the claim was met with real skepticism from parts of the physics community, with some researchers arguing the evidence fell short of proving the underlying particle, a Majorana quasiparticle, had actually been observed. Microsoft has continued to defend and refine its results, but the episode was a reminder of how difficult it is to separate genuine breakthroughs from optimistic marketing in this field. And then there's PsiQuantum's bet, photonic qubits, encoding information in individual particles of light. Photons are naturally resistant to some forms of noise since they barely interact with their environment, and they can travel through fiber optics, potentially making them easier to network together at massive scale. The trade-off is the opposite of the others. Because photons barely interact with anything, getting them to interact with each other in a controlled way, which is what a computation actually requires, is extraordinarily hard. It's why PsiQuantum has made a very different bet than its rivals. Instead of trying to perfect a small machine first, the company has gone all in on manufacturing scale from day one, partnering with global foundries to fabricate its photonic chips using existing semiconductor production lines. In January, NVIDIA CEO Jensen Huang told investors at a conference that truly useful quantum computers were probably 15 to 30 years away, a timeline far more conservative than many quantum companies had been promoting. The comment wiped billions of dollars off the market value of publicly traded quantum firms in a single trading session. Dr. Elena Marsh, when the CEO of the company that basically defines the AI computing boom says quantum is decades out, people listen. It doesn't matter that he later walked it back a bit. The market had already voted. Huang did later soften his comments, acknowledging that some quantum applications could arrive sooner than his original estimate. But the episode exposed something real. Much of the valuation in quantum computing today rests not on demonstrated, repeatable, commercially useful results, but on the promise of what these machines might someday do. That promise has been tested before. IBM, Google, and others have each announced experiments demonstrating quantum advantage. Instances where a quantum processor completed a specific, often narrowly engineered, calculation faster than a classical supercomputer could. Google's Sycamore processor made headlines for this back in 2019, and newer, more capable chips have repeated similar demonstrations since. But critics have repeatedly pointed out that these tasks are often chosen because they're hard for classical computers and easy for quantum ones, not because they're useful. Simulating a genuinely difficult drug interaction, optimizing a real airline's global logistics network, or breaking modern encryption remain well out of reach. Add to this the sheer scale of investment pouring into a technology that hasn't yet turned a meaningful profit, and it's easy to see why some analysts worry about a bubble. Quantum computing stocks have swung wildly, soaring on incremental technical announcements, then plunging on comments like Huang's, or on disappointing quarterly guidance from the same companies driving the hype. Dr. Elena Marsh, nobody remembers this, but early classical computers were incredibly unreliable too. Vacuum tubes failed constantly. The first transistors were noisy and inconsistent. We didn't wait for perfect error-free computers before we started using them. We found problems they were good enough to solve, and we improved the hardware around real use cases. Industry advocates argue quantum computing may follow a similar path, not a single dramatic leap to a perfect, fully error-corrected machine, but a gradual climb through what some researchers call utility scale or industrial quantum advantage, a stage where quantum processors, even with some residual noise, can outperform classical methods on specific, valuable, real-world problems in chemistry, materials science, or optimization, well before full error correction is achieved. Several executives in the field have pointed to a window of 12 to 18 months for the first credible demonstrations of this kind of industrial quantum advantage. Narrow but genuinely valuable use cases, rather than sweeping, general-purpose quantum supremacy. It's a bet PsiQuantum is backing with concrete, poured concrete. In Illinois, the company is building a $500 million quantum computing campus, with state and local backing, aiming to house a utility-scale machine built from millions of qubits. In Brisbane, Australia, PsiQuantum and the Australian government are jointly funding a $620 million project with similar ambitions, a sign that governments, not just venture capitalists, are willing to make long-term, sovereign-scale bets on this technology. PsiQuantum executive, paraphrased on camera, "We didn't want to build another lab demo. We wanted to build the thing that comes after the demo, a machine designed from day one to be manufactured at the scale semiconductors are manufactured at today." That manufacturing-first philosophy is, in many ways, a direct response to the industry's biggest structural challenge. Today's most advanced quantum computers still have only a few hundred qubits. Getting to 1 million or more, the scale many researchers believe is needed for broad, fault-tolerant, general-purpose quantum computing, isn't just a scientific problem anymore. It's an industrial one, closer to building a new kind of semiconductor fab than running a university physics lab. Forecasts vary wildly depending on who you ask and what they're counting as useful. Some researchers point to narrow scientific applications, like simulating small molecules for drug discovery or optimizing niche financial models, arriving within the next few years. Broader, transformative impact across industries, the kind that could reshape entire sectors of the economy, is more commonly projected toward the end of this decade, with several forecasts converging on major measurable value creation by 2029 or shortly after. Dr. Elena Marsh: I think people want a single yes or no answer, and this field just doesn't have one. Different architectures are going to hit different milestones at different times. Some narrow applications might genuinely work within a couple of years. Full-scale, fault-tolerant, general-purpose quantum computing that changes everything, that's probably still most of a decade away, maybe longer. That uncertainty is uncomfortable for investors who have poured billions into the sector expecting near-term returns. But it's not unusual for foundational technologies. Consider self-driving cars. For years, autonomous vehicles were dismissed by many serious engineers as a fantasy. Decades away at best, impossible at worst. Early demonstrations were clumsy, expensive, and unreliable. Skeptics pointed, reasonably, to the enormous gap between a controlled test track and the chaos of a real city street. And yet, gradually, the technology closed that gap. Not through one single breakthrough, but through years of incremental engineering, better sensors, more data, more computing power, and enormous patient capital investment that didn't pay off for a very long time. Quantum computing may be following a similar arc, dismissed by some as impractical, defended by true believers as inevitable, and, in reality, grinding through the unglamorous, expensive, difficult middle phase that most transformative technologies have to pass through. But that gap between the lab and the real world is exactly where this story is being written right now. Between the billion-dollar hype and the billion-dollar skepticism sits an industry racing to prove that the strange, fragile, powerful physics of the quantum world can be tamed. Not perfectly, not immediately, but well enough, soon enough, no matter. The question was never really if a practical quantum computer is coming. Increasingly, across labs from California to Illinois to Brisbane, the question the industry is racing to answer is simply, when?